Okay, this is part 3 of our Introduction to Power series. And we saw in part 2 that we took a function, we used cosine of x, and by playing around with the value of the function at 0 and the value of its derivatives at 0, we were able to find a0, a1, a2, a3, a4, etc., which are the coefficients, the numbers that multiply the various powers of x. And we've written that out in shorthand, which is using the sum notation, and in longhand. So what we're going to do is generalize this to get a general formula that you can use for any function. So the idea is you're given a function, you have to find the a's. That way you have the power series expansion, and if you cut it off at a certain point, you get a very good approximation for the function. So let's observe that f of 0 is equal to a0, because when I plug in x is 0, all these terms go away except for a0, because they'll have an x or an x squared or an x cubed in them, etc. And so now I know a0. Well, how am I going to find a1? The way I'm going to find a1 is the way we did it with the cosine, is we're going to take the derivative of both sides. And the derivative would be a1 plus 2a2x plus 3a sub 3x squared. I'll write the next one. Plus 4a sub 4x cubed, and it keeps going. Now you'll notice that if I plug in x equals 0 again, I'm going to get a1. So f prime of 0 is equal to a1. So now I have a1 by taking the derivative and setting it equal to 0. Let's go back to the derivative and take the second derivative. So the second derivative of x would be 2a2 plus 6a3x plus 12a4x squared plus dot dot dot. And now I can find a2. In fact, f double prime of 0 is 2a2, which means that a2 is f double prime of 0 divided by 2. Okay, let's try it one more time. Let's take the third derivative. 2a2 goes away, and we would have 6a3 plus 24a4x plus dot dot. And again, we plug in 0, and we get an equation for a3, and we get a3 is equal to f triple derivative, third derivative, divided by 6. Now you notice what's going on with these numbers. The reason these numbers are appearing, we have to keep taking derivatives of the powers until we get down to 1, basically, or 0. So we take, for example, if we started with x to the 4th, we would take one derivative, would be 4x cubed. Two derivatives would be 4 times 3 times x squared. Three derivatives would be 4 times 3 times 2 times x to the first. And then one more derivative, 4 times 3 times 2 times 1. And there's a special name when that happens for a number, and that's called a factorial. So we define n factorial to be n times n minus 1 times n minus 2 all the way down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. So you'll notice that these numbers in the bottom really are factorials. Let's do one more. Let's do the fourth derivative. Well, that equals 24a4 plus, there's some other terms here, which are all going to be 0 when I plug in x equals 0. And then when I plug in x equals 0, I get 24a to the 4th, and 24 is 4 times 3 times 2 times 1, so a to the 4th is f, the fourth derivative at 0 divided by 4 factorial. Now you can see we can keep doing this. And the general rule, of course, is that the a sub n is going to be the nth derivative at 0 divided by n factorial. So that's the way we can get all of the a sub n's, the numbers that express the expansion of the function as a power series in x. And so the general rule, we're going to take all these a sub n's and put them in. This way, f sub x is going to be f sub 0, because that's a0, a plus the first derivative at 0 times x, plus the second derivative at 0 times x squared. And we have to divide by 2. We'll call that 2 factorial, which is the same as 2 times 1, plus the third derivative at 0 times x cubed, divided by 6, which is the same as 3 factorial, plus the fourth derivative divided by 4 factorial, and it keeps going like that. That is called the Maclaurin series. It's a special case of the Taylor series. We can write it out in a closed form. Where it's understood that f of 0 is just f. That is, when you put the 0 here, you don't take any derivative at all. And it's just the value of the function at 0. And then the others are the first and second and third and fourth and fifth and sixth derivatives, etc. Now there's another thing that's kind of interesting about this. If you take the first two terms, you get f of 0 plus f prime of 0 times x. Now what is that? That is those first two terms. There's more terms, which we'll forget about them for a second. That's the tangent line. That's the tangent line at 0. This is the slope at 0. This is the intercept at 0. This is, in fact, the tangent line. So it starts out with a tangent line, and then it has all kinds of additional corrections or additional pieces that make it more and more accurate. Okay. All right, now that we have that formula for the Maclaurin series, let's just do one more thing, which is to find start with a couple of functions and find what the series looks like. Well, we already did the cosine. So the cosine looks like this. I'm going to write it out in the Maclaurin series version. That's 4 factorial minus, it turns out, 1 over 6 factorial x to the 6th plus 1 over 8 factorial x to the 8th. Because that's the pattern. So it's plus, minus, and only even powers, and you get these factorials. Let's try something else, which is pretty easy, actually. Let's try e to the x. In order to write out the power series for e to the x, we're going to have to know f of 0. This is f of x. We're going to have to know f prime of 0. We're going to have to know f double prime of 0. We're going to have to know f triple prime of 0. Well, the derivative of e to the x is e to the x. And the value of f e to the x when x equals 0 is 1. And the derivative is still e to the x. And I evaluate that, and I still get 1. And when I keep doing this, what's going on, don't forget, evaluate that at x equals 0, I get 1. And that's true for the function itself and all its derivatives. So e to the x is a very special function whose derivative is equal to itself. And so the Maclaurin series for e to the x must look like this. Each time I have a 1, then I have an x to the n over n factorial. Because the coefficients are all 1 over n factorial. because don't forget a sub n is the nth derivative at 0 divided by n factorial. And that's what's going on here, which is the same as 1 plus x squared plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. And that's the expression for e to the x. Let's do one more. Let's work out the sine of x. Well, we have to know the derivative of the sine of x. First, we have to know the value of the function at 0. So sine of 0, of course, is 0. And its derivative is the cos. And we evaluate that at 0, we get 1. That's the first derivative. This is the function at 0. This is the first derivative at 0. The second derivative, of course, will be minus the sine at 0 equals 0. And the third, so this would be the second derivative at x equals 0. And the third derivative at 0, of course, is the derivative minus sine, which is the cos, minus the cos, so I get minus 1. So it looks like this. Sine looks like this. It starts off at 0 plus 1 times x. Then you have an x squared, which isn't there, minus 1 times x cubed, but you have to divide by the 3 factorial, because don't forget a3 is f triple derivative at 0 divided by 3 factorial. And this goes plus or minus 2. So the next one would be x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So you notice the sine, which is odd, only has odd powers. And it has all the powers that the missing on the cosine, and it goes plus minus plus minus plus minus just like the cos does. And you can check that this is a very good approximation for the sine. In fact, if you just did x minus x cubed over 3 factorial, you'll get an excellent approximation for the sine in radian measure. Okay, that's all for today. But I want you to remember, let's write it one more time. The Maclaurin series for a general function f of x is going to be the value of the function is 0 plus the derivative at 0 times x plus the second derivative at 0 times x squared over 2 factorial plus the third derivative over 3 factorial. And that's how it works. And if you can remember that formula, you'll notice that as long as you can take derivatives of some function, if you start with a function f of x and you can take derivatives, then you can do this. You can't do it if you can't take the derivative. So there's some functions that this doesn't work for, but so-called smooth functions where you can take a lot of derivatives, in fact, hopefully all the derivatives, it never stops. You can do this, and this is the formula for the Maclaurin series.